So chapter 4, section 4.1 is brought to you by Lego Dementor, I believe, from Harry Potter. Okay, so in this chapter, we're going to be learning all about quadratic and then higher ordered polynomial functions. Just as a reminder, I think we mentioned this, the linear equation, y equals mx plus b, is a polynomial. We're going to talk about how this is a first degree polynomial. So we already know some stuff about polynomials, but now we're going to look at this, specifically the quadratic formula, or the quadratic function, which you may recall the quadratic formula from high school days. And then we're going to look at polynomials that have a higher order, meaning cubics and quartics and beyond. So our authors begin with a discussion of the Willis Tower, which I guess it was formerly called the Sears Tower in Chicago. It's a quite tall skyscraper. And you're going to go climb to the top of this tower. I actually had a chance of doing that once, and it's quite high up there, and you ride an elevator up, and everything's enclosed, and you look down. And so what they're describing here you couldn't do, but pretend you could drop a ball from the height of this building. Now it's 1,450 foot high building. So here's this equation that models it, and you can see this height, 1450, came from the height of the building. And then this negative 16t squared, this t is time. And so after 0 seconds, so before we drop the ball, or right before it, the height would be 1450. And then as time passes, we're going to be, the height of the ball is going to decrease. Notice it's negative 16 times the time squared. You might know some things about gravity, which is where that negative 16 comes from. So we're supposed to sketch a graph of what this would look like. So, I don't know, here's our tower, and we're just dropping the ball, and it's just going to go shoop like this. And we might note that this is 1450. This down here is 0. So if we wanted to, we could put an x and y axes on here. And we could call this part would be 0 height. This point here would be 1450. We can't really do an x and y axis on this because this would be t and this would be h of t. So we would have to change this. We can't just show this 1x value dropping. We'd have to make it look something like this for it to make sense in x and y axis. So our authors then say, hey, let's fill in this table for all of these times. Well, anytime I see this, and I'm given a function, I don't want to do any of this mess by hand. I'm going to let the technology do it for me. So let's jump to Desmos. We'll type in our function here. I'm going to use x's. Desmos tends to prefer x's over t's. And our function was negative 16 t squared, notice I'm using x, plus 1450. Now, whoops, I got an equal sign there. We're not particularly interested in the graph right now, although that is all of the ordered pairs. What we want is the table. So I'm going to insert a table. Nope, that was an expression. Let's try again. I'm going to insert a table, and I'm just going to write here hx1. So now I'm telling Desmos, use this as the function, and then I'll put in all the values they wanted. They want 0 to 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's the heights. Notice at 10 seconds after we drop this ball, we're at negative 150 height. What would that mean? Well, that would mean we've gone below the sidewalk, if you will. So that value probably doesn't make any sense. Okay, back to our textbook. So we filled in our table using Desmos. Now we're going to answer a few more questions. So for B, it says, how far does the baseball fall during the first second? Well, for that answer, we just look at the difference between the heights. So h of 1, let's do h of 0 is the height of 1450. That's the height of the building. And then h1 height after 1 second of falling, it's 1434. So the total distance that this ball has traveled, or fallen, is the difference between these two. 1450 minus 1434. That happens to be 16 feet. Then we're going to say, well, how far does it fall during the interval from 1 second to 3 seconds? That's question C. So our height after 1 second is 1434. Our height after 3 seconds is 1306. And we'll just get the difference between those two. 128 feet. All right. That seems to be a lot more. Of course, we've done 3 seconds than the distance between these, or we've got a total of 2 seconds in between. All right, so question 3, we're going to continue to kind of run through this. It says use the height function. All right, let's write that down. H of t equals negative 16t squared plus 1450 to determine the average rate of change of h with respect to t over the given interval. So average rate of change is, as the book gives us, change in output divided by change in input. I would write that as delta y over delta t. That delta is a Greek letter that stands for change, often in the physics world. So for A, we're to do this from the first second to the second second. Well, we already did that. Up above, we found there was a 16-foot change. But what we want to do is write it this way: 1434 minus 1450, and then 1 minus 0. This would get us negative 16 feet in 1 second. Or how we might write this is negative 16 feet per second. That's another way you could write it. All right, and then B, we're doing the same thing. We calculated this already before. So we had 128-foot change between the two. That's how far it dropped. So I'll do the 1306 minus the 1434. That's the change in y's, divided by the change in x. 3 minus 1. I mean t here is really what it is. So this ends up being, we had a 128-foot drop over those two seconds. And if we simplify that, we get a 64-foot drop per second from the first second, or from the first second to the third second. Okay, so then C says, all right, is this a linear function? Well, we could have said, of course not. We know linear functions do not have exponents above a 1 from what we've talked about before. But looking at this average rate of change, we'd say no. The average rate of change is not constant. That's the key indicator of a linear function. All right, so let's look at number 4. Number 4 says, what is the value of h when the baseball strikes the ground? Okay, so let's think about what that means. H of t represents the height of the ball. T is time in seconds. So when they say, what is the value of h, they're saying, what is the height of h when it strikes the ground? Well, that means it should be at 0. If we were 1,450 feet above the ground, that means it would be a 0 value. So then we've got to figure out, well, when is that? So if we look back at our table in Desmos, we can say, well, it's between second 9 and second 10. And this is where the graph becomes super awesome. We could go straight to this graph, and we could see it right there. We can get a more precise value. Bam. Oh, by the way, notice what I did. I hit the zoom fit button, and that zoomed us to the points on our table, and it gave us a nice picture of this graph. There's another really obvious indication this is not a linear function. There it is. It's at 9.52 seconds. That's when the graph is telling us that that the ball hits the ground. So if we wrote it in that function notation way back from chapter 1, we'd write it like this: h of 9.52 equals 0. All right, that's A. So then B says, well, what's the practical domain of this thing? In other words, what are the t values? Well, if you look at that graph, the only t values before 0 don't make sense. Maybe we could make some sense of it because you have to get to the top of the building. So if we made 0 the moment we made it to the top of the building, going backwards in time would be getting on the elevator. But really, that's just stretching. So we know it needs to be from 0. And then once the ball hits the ground, there's not really much else it's going to do. If we think back to the logarithms thing, it'll bounce a little bit. But eventually it'll stop and it'll just stay stay on the ground. And if it's falling from a 1,450 feet, it might just get embedded in the ground and not even bounce. So that means the domain, or the possible t values that make the most sense, would be this. Or if we wrote it in interval notation, we'd use bracket 0, 9.52 bracket. And then what's the range? What are the y values or the h values that make sense? Well, that's the 0 value when the ball hits the ground, and then the height of 1450. If you look back at this graph, is nothing above 1450. No h value or y value exists. So it's this really to negative infinity is the domain of this function. But when we're talking about practical domains, anything below 0 doesn't make sense. It would be underneath the ground. Yeah, we're just reaching to try to make up something for that. So that practical domain would be this, or sorry, range, or in interval notation, we would write it again as bracket, 1450. You'll just have to watch for which version of this MyMathLab wants it in. And then D says, let's take a look at the graph, and I'm just going to say here, see Desmos. Don't draw things by hand when you can let Desmos do the thing for you. All right, and then our final question here with this problem says, is the graph of the height function in part D the actual path of the object? And that's going back to this graph we drew before. When we think about what's happening, the ball is just dropping. So here's the ball dropping. But when we graph this on an x and y axis, really a t and h of t axis, we have to show the progression of time, 0, 1, 2, 3, 4, 5, 6, blah, blah, blah. So we can't have the ball, the actual path of the ball show up on this graph. It wouldn't be a function. It'd be this vertical line like this, and we know that's not a function. There's infinite outputs for that one input. So the answer here is no. The graph is showing the height of the ball with respect to time.